ఓపెన్ చేస్తాను.
లాగిన్ సో అప్పుడు మెయిల్ పెట్టాను సార్ మెయిల్ మీకు పెట్టి వచ్చాను
పెట్టేసుకోండి. ఇప్పుడు స్ట్రీమింగ్ అవుతుంది
అంటే బ్లాంక్లో ఉంది స్ట్రీమింగ్ అవుతుంది.
ఈ స్క్రీన్ రావాలి కదా మనకి. వచ్చింది.
దీనిలో మీ మెయిల్ వస్తుంది.
నాకేది లేదు సార్. నరసింహ సార్ మీది మెయిల్
జస్ట్ మెయిల్ వస్తుంది.
సార్ మీది
ఇది
ఒకసారి లాగా క్యాప్స్లో కావాలి. మేడం ఒక 5 minutes జాయిన్ అవ్వండి. అదేనమ్మా వస్తాయా అంటే ఎలా చెప్పగలను చెప్పండి. మోస్ట్లీ అయితే యాడ్ చేయండి. అప్పుడు మీకు 2 days వచ్చాయి కదా, ఇప్పుడు 3 వస్తాయి. నా క్యాబిన్లో పెట్టండి. ఎందులో నేను మెయిల్ అడిగాను. సిగ్నిఫికెన్స్
అంటే బోల్డ్ ఉంది సార్ యూట్యూబ్ ఛానల్ అలాగే
అవును
కానీ
హెవీ స్వీట్ అవును.
హెవీ అంటే హెవీ.
ఇప్పుడు నీకు ఒక లింక్ పెడతాను, అది గ్రూప్లో పెట్టేసి ఎవరికైనా లాగిన్ అవ్వకపోతే అది యూట్యూబ్ లైవ్ ఛానల్ అని చెప్పి.
ఓకే
నువ్వు ఇది స్టార్ట్ అయిన వరకు ఉండమ్మా. నీది ఏ మొబైల్ రా? మోటరోలా? ఇదే కదా మన స్క్రీన్ ఉంది. ఇక్కడ ఉన్నది కూడా అదే.
ఇది అంటే అది వెయిట్ మరి సెలెక్ట్ చేయగలరు. అది పూరి తీసేయండి సార్. డిస్టెన్స్ కూడా తీసేయండి సార్.
క్లోజ్ చేసి
అంటే 5 seconds 10 seconds ఇదే ఉంటుంది కదా. ఇందాక వచ్చింది ఇప్పుడు ఎవరో జాయిన్ అయినట్టు సార్ జాయిన్ అయినట్టు
ఇందాక ఇప్పుడు మనం ఈ స్క్రీన్ ఇచ్చాం కాబట్టి ఇదే ఉంటుంది. ఇప్పుడు దీనికి వెళ్ళినా అది రాదు కదా.
రాదు సార్, కానీ చూడండి ఒకసారి.
అది ఎందుకంటే మనం ఇదే ఇచ్చాం కాబట్టి ఇదే
అదే
వస్తుంది.
అదే చెప్పాను కదా సార్, ట్యాబ్ ఇస్తాము, ఎంటర్ స్క్రీన్ ఇస్తాము. ఎంటర్ స్క్రీన్ ఇస్తే మొత్తం వచ్చేస్తుంది, ట్యాబ్ మాత్రం ఇచ్చాను కాబట్టి
ఇది ఒకటే
ఇదే
వస్తుంది.
వస్తుంది. వచ్చింది. ఒకటే ఇచ్చాను.
సరేలే, మనది మనం కదలకుండా ఉంచేస్తే సరిపోతుంది.
మిగతా మనం తీసింది.
ఇంకోటి ఏదో ఉంది కదా అసలు. దేని నుంచి రీడ్ అయ్యింది ఇప్పుడు మనకి? మైక్ ఆఫ్ చేసిందా?
ఈసారి మాట్లాడినట్టున్నాను సార్. మైకు ఇది పెట్టుకోండి. ఎవరు మాట్లాడుతున్నారు?
మైక్ ఆన్లో ఉంది.
సార్ లైవ్లో ఉంది, ఇప్పుడు పర్లేదు. తెలిసి ఇంకో మెయిన్తో ఓపెన్ చేస్తారా సార్? అంటే ఇప్పుడు సిఎస్ అంటే ట్యాబ్ ఇచ్చాం కదా, ఈ ట్యాబ్ ఇచ్చిన తర్వాత ఇక్కడ ప్లస్ కొట్టి మనం అది ఓపెన్ చేసాం కాబట్టి ఆ ట్యాబ్ వచ్చింది, కానీ వేరే దాని నుంచి ఓపెన్ చేసి రాదేమో, ఇది రాదేమో నాకు తెలిసి. చూడండి ఒకసారి. ఇందాక ట్యాబ్ ఇచ్చాం మనం, అంటే వేరే దాన్ని తీసుకోకుండా దానిలోనే ఇచ్చాం కాబట్టి
రాలే. ఇందాక నువ్వు అన్నట్టు అక్కడ ఇచ్చాం కదా,
ఆ ట్యాబ్తో ఓపెన్ అయిపోయింది కాబట్టి అది వచ్చింది, లేకపోతే రాదు కదా.
ఇది రాదు.
సో అదే
అది ఆ స్క్రీనే కదా, అది ఆ స్క్రీన్ ఆ క్యాప్చరింగ్ దాంట్లోనే ఉంది
కాబట్టి.
వాయిస్ ఎక్కడి నుంచి వస్తుంది నాకు అర్థం కావట్లేదు.
సార్ చెప్పండి సార్. రమేష్ సార్ దగ్గర ఉంది సార్, వస్తాను ఒక 5 minutes. ఎక్కడ ఉన్నారు? ఏ బ్లాక్ సార్? ఓకే ఓకే సార్. నేను అలా ఇనాగ్రేషన్ ఉంది సార్.
అది అయ్యాక వచ్చేస్తావు.
సరే సార్,
ఎంత
అంటే 15 minutes అవ్వదు.
సరే, అది అయినాక ఇమీడియట్గా వచ్చే.
సరే.
ఎందుకంటే ఈ మధ్యలో ఏమైనా నేనేం చేయలేను.
అదైనట్టు వచ్చేది.
ఇది ఇలా ఉంచేస్తాను, ఇంకేం చేయను. మేడం స్టార్ట్ చేసేయండి. మేడం మీది ఏమవుతుంది పేరు ఇక్కడ? మాధురి కదా, కో హోస్ట్ ఇస్తున్నాను మీకు. కో హోస్ట్ ఇచ్చాను. అదే మేడం స్టార్ట్ చేయండి, అదే చెప్తున్నాను కదా నేను.
Good afternoon to everyone. A warm welcome to esteemed guests, faculty, colleagues, and participants of our 5-day online faculty development program. I am K. Madhuri, Assistant Professor in CSE Department. I am delighted to welcome you all to Day 2 of our online faculty development on quantum computing and machine learning, bridging quantum theory and intelligent systems. Yesterday, we had a wonderful beginning with an insightful session on the basic general trends of quantum computers, and we able to understand simple quantum circuits, build and run simple quantum computing tasks with Qiskit, and had some excellent discussions. Thank you all of your active participation in really made the day meaningful. Today we continue our learning journey with more enriching concepts in the quantum machine learning domain. It is my honor and privilege to introduce our eminent speaker, Dr. Kaushik Shekaran, whose presence brings great academic weight and research insight to this event. Dr. Kaushik Shekaran is an accomplished academician and researcher with 17 years of teaching experience in the field of computer science and engineering. He is currently serving as an associate professor at MT School of Engineering and Technology, MT University, Hyderabad, and also works as adjunct faculty at Universidad Juárez del Estado de Durango, Mexico. He completed his BTech in Computer Science and Engineering from Sastra University in 2005, followed by an ME in CSE from Medco Shillong Engineering College, affiliated with Anna University, graduating with first class with distinction in 2008. He earned his PhD in Computer Science and Engineering, specialization in cloud computing from WIT University, Vellore in 2015. Dr. Kaushik has an impressive research portfolio with 35 plus publications in high quality SCI and Scopus indexed journals, conferences, and book chapters. He is an active member of IEEE, a recognized speaker, and is known for inspiring and motivating young learners. He also contributes to the research committee as a reviewer for several reputed international journals, including IEEE Internet of Things and the Journal of Supercomputing. His primary research interests, including cloud computing, deep learning, and Internet of Things. His academic profiles are available on Google Scholars, Scopus, Web of Science, and Vidwan, reflecting his strong research footprint and global academic engagement. Before we begin, a gentle reminder to keep your microphones muted, use the chat box for your queries, and keep your camera on if possible for better interaction. Ladies and gentlemen, please join me in extending a warm and delightful welcome to Dr. Kaushik Shekaran. We look forward to his talk and are confident it will open stimulating perspectives that enrich our understanding and guide our research and teaching endeavors. Sir, over to you.
Yeah, thank you for the very warm introduction, Ms. Madhuri ma'am. and I'm really happy and privileged to attend this wonderful session, FDP session on quantum and machine learning concepts. So thank you for the profile description about me, and really I'm happy to hear. And I'm really happy, I'm appreciating the participants for their patience listening. Anyway, I think yesterday it started and we are continuing the journey on quantum. So today, up to what level I can deliver the best, I will do it. And I thank every one of the organizer, coordinators, and Mr. Panduranga Vittal sir for inviting and scheduling the meeting in this. And also thanking Aditya Institute for Technology and Management for the opportunity you have given to me. Thank you very much. And can we start the session, or can I wait for some more participants to join?
Start it, sir.
Okay, sir, sure. So now I think my audio is clear, right? Audible?
Clear, sir. Clear.
Okay. So I will now share the screen. Can you please confirm it whether it is coming or not? And also I will be switching off my video during my sessions. And while interacting session, again I will switch on video because for bandwidth issues. Okay, now I will. Yeah, I shared my screen. Please tell me, is it visible?
No, sir. Yes, sir.
Okay. Okay, thank you very much for the confirmation. Okay, thank you, and we'll start the session today. So today session is on quantum algorithms, especially Deutsch, Joshua, and Grover's algorithm. I'm going to explain step-by-step process. Before that, I think I have to tell the basics of what is quantum and how quantum algorithm evolved, and now where are we? Okay, and also will tell the implementation part of it, and also I will give you some few techniques how to work with the Qiskit implementation, and also I have some simulation for these two algorithms. Okay, so we will go in the later part. First, we will see clearly what is what, because these two algorithms are one of the important algorithms from starting 1992 onwards, and we will look onto it. Okay, so myself, Dr. Kaushik Shekharan, I am right now in associate professor working in Amity, recently established campus in Hyderabad. And I have some experience, and last 7 years I'm working with quantum, and I have published few research papers on quantum, mostly in cloud IoT, and recently I started in quantum. Okay, so about quantum, but before telling this, I want to tell you all about what is quantum and why quantum is necessary, and how can we understand the quantum. Okay, so he is what we are seeing here. He is Richard Feynman. So he himself told that those who understood quantum fully, that means they did not understood quantum properly. That means it is we have to understand as well as we have to imagine for the proper implementation of quantum. Quantum is a bit confusing, but if you understand by thinking in the quantum way, you can get it. Why people are not understanding quantum is they are thinking in classical way and trying to understand quantum. Suppose, for example, we have zeros and ones in binary, but in quantum there is 0, 1 and 0, 1. So it is qubit. So usually quantum will have a different state and different dimensions. So we need to understand it very carefully as well. Okay, so in 1959 there are some glimpses of quantum started in quantum mechanics and quantum physics. In 1981 there are some quantum physics where they started implementing in through quantum computations and quantum computing technologies. Okay, so this excellent scientist Richard Feynman, he played a crucial role in launching quantum as one of the emerging technology in the 1980s. Then later, after that, lot of research papers started coming into quantum, and we will also see the evolution why we are having this many quantum algorithms or this many quantum ideas. Okay, so in 1985, after some time, David Deutsch, we have to spell like Deutsch. David Deutsch, he is a physicist. He published his first theoretical proposal in quantum computation. He was basically a theoretical physicist where he started working in mathematics concept from Turing machine. I think you know about Alan Turing. Even Turing Award is very famous all over the world. So he started implementing the quantum, and he started working with qubits as well. So he started working with logical gates along with qubits. So he created two important gates. One is called Hadamard gate, and one is called C0 operation that we will see later. So his approach was very straight and very straightforward of photonic physics and atomic physics, where he started working on how the electron theory, like how an electron revolves around nucleus, how it is going to one state to other state, and how it is going to excitation state, and how much time it is staying in excitement state, and how can we map this photons in a quantum way. So that was his idea, and he started implementing few of the algorithm that is called Deutsch algorithm initially, and later he collaborated with one more scientist called, I will show that slide. Yeah, Richard Josser. So this scientist had already worked with quantum few years back, and he collaborated with David, and they created Deutsch-Josser algorithm. It is solving a lot of problem from classical computer to quantum computer in less time. So that's why this algorithm is one of the biggest hit that time. So what they did is they were trying to solve some problems such as suppose factorization problem, and also some of the problems that is unsolvable that time. So they were trying to solve it with their less time, such as there are some classical problems such as Avogadro numbers, and there is Fibonacci numbers. If you keep on increasing the factors, it will go in the n terms. But the problem is that time no one told to what is the upper limit for them. So they started giving the formula and idea for solving this problem. So eventually in 1993, two more scientists, Ethan Bernstein and Umesh Razirani, they also started working with like quantum error corrections. That also I will tell later. So, and again, Daniel Simon also showed how the exponential speedup happened for a particular function in classical computing, how it is working better in quantum computing. So these are all some breakthrough on that time. And again, one more algorithm that is called Shor's algorithm. This scientist called Peter Shor, in 1994, he started deploying this algorithm. It is like factorization problem, like very fast factorization the quantum computing doing because of Shor's algorithm only. Because even though David Deutsch and Joshua proposed DJ algorithm, but that is only for finding constant and balanced versions. But what Peter Shor proposed was, he was completely a mathematician as well as computer scientist. He involved most of the linear algebra and cryptographic methods for solving factorization very quickly. Even recently also in China, there are few scientists trying to break the RSA because they want to prove that quantum computer is faster than the classical computation. So in that time, what they did is they started doing that. Eventually, they started breaking RSA only up to 8 bits. Even that 8 bits was a breakthrough in the recent times. In 2022, they started deploying. But why we are not seeing the full potential of quantum is there is one more concept called qubits that I will explain you later. But here what Peter Shor found out was the factorization can be done very fastly, and it can be done very quickly as well, because we are using some gates and we are using some methodologies that is called Oracle that I will explain you. So he used for speed up the process, and now we are using that for cracking some encryption methodology such as even AES. Okay, so this Shor's algorithm also very much popular on that time, until we are using that for breaking some cryptography. So that nowadays many research papers are coming like post-quantum cryptography. That means already quantum started arriving, or we can say arrived in the world, because Google started Google supremacy, and IBM, they have their own quantum computing, Microsoft Azure quantum, like lot of tech giants, they started their quantum machines. So they are implementing these algorithms for their efficiency of their machines. Suppose IBM already tested this Shor's and Grover's algorithm in their IBM quantum machines, and they proven that they have less time for solving the very big complex quadratic problems. And they have also tested with like simple problems as well as the bigger problems. They have also told about the space complexity as well as time complexity. So it is one of the way we can understand. Also, I told quantum has arrived means in the near future, surely the quantum computing going to take over, because it may not immediately, but eventually it may happen, because just 10 years back we don't know much of AI, but now most of the users are using generative AI, explainable AI, and lot of predictive models. Even in medical healthcare we are using the predictive model. So that means AI already into the picture. Like that, quantum now, it's already the era has been begun. Now we are seeing the outcomes. So sure, in next 50 or 100 years we can see a lot of advancements in quantum. So the complex problems will be getting solved very easily in less time. That's what Peter Shor told us. Next is Grover's quantum algorithm. Just I'm giving a few brief definition of who invented and what is what, and later I will go detail about what is DJ, Deutsch algorithm, and also I will tell about Grover's algorithm in detail. I will also tell step by step how to understand these algorithms. Okay. So Love Grover, he is like Indian. He got settled in US and Canada, and he is actually a Punjabi, like Love Kumar Grover. Okay, so he created in 1986 called Grover algorithm, where it is using for quadratic split of unstructured data. That means usually in linear search what we used to do is we are going to search an element in a number of elements. Suppose if we are having 100 elements, say for example, so we used to search one by one, maybe binary search or linear search or so on. So what may happen, we need to work out one by one. That will take order of n, right? Big O of n. So that time the complexity is, the worst case complexity is very high. That means we need to wait so long time to get the result, right? So that is the problem in the existing search algorithm. So in 1996, what Grover developed was search among unstructured data with quadratic speed. That means he was using the Hadamard gate. That's called Hadamard gate concept. He was using that multiple times. And also he came up with one concept called reversible quantum computing, that I will tell you. So this is one of the second major algorithm after Shor's algorithm. And now recently they implemented, like 8 years back, in 2017, they implemented in IBM machines. And right now this Grover's algorithm is used in many of the USA logistics companies, because this algorithm is solving many optimization problem and also supply chain logistics problems. Very fastly we can able to access the data. Even Amazon, whatever the products you are ordering online, it is following, that's called Amazon bracket model in AWS, that is solving using the Grover's machines, Grover algorithms. So this is what one of the breakthrough in that time, 1986, and still we are using that. Then next scientist called Seth Lloyd in 1996, he proposed quantum algorithm that is for simulation purposes, like simulating the quantum mechanical systems, such as for drug discovery and also for memory sites, and big operations can be solved very easily. So he was one of the early going for simulations. And even the QuizKit that are all recently developed by IBM, but the first simulations in quantum made by Seth Lloyd, such as for drug design. That means the pharmaceutical companies are going with that, and material science, like strength of materials and thermal conductivity on materials. These kind of things we have to simulate first. So using quantum simulation, it will be faster and very accurate. And also such as high energy physics applications such as CERN lab in Switzerland, they are working with Seth Lloyd simulation methods. That means for atomic physics simulations, we need to first understand and estimate how much molecular or nuclear energy is needed. So that is very important. So these simulations helped us to understand how the quantum process and how it can work. Okay, so these are all number of algorithms. Now we'll see the evolution and what is the goal of study of quantum algorithms. Okay, so now find problems with quantum computer solves faster than any classical computer. So classical computer means whatever we are using right now, like desktop or laptop or even your mobile, these are all coming under classical computing. That means whatever we are giving input, it is giving output. So it is like a input and output processing, same like we are following the von Neumann architectures till now. Maybe the technology name changes or the architecture name changes, but the base is same. Such as, you know, the von Neumann architecture in 1960s, he created the RAM, ROM, and other input-output models. Still, we are following the same, right? So this is called classical computing. But what is quantum computing is, in quantum computer, there is no separate components, but rather we have lot of logical components, such as qubits, its logical component, and input-output also not exactly like what classical computer does. So in classical computer, we have zeros and ones, we have AND gate, NOT gate, NOR gate, OR gate, XOR gate. But in quantum, we have CNOT gate, we have AND gate, we have quantum gate, we have Hadamard gate. That means the output will not be predictable and input can be reversible. That I will explain you in slides, in the coming slides. So these are some of the things. Earlier people were not realizing about the power of quantum, like Deutsch, Joshua and Simon. That time people they're trying to prove how to prove the quantum algorithm through in a mathematical way for proving that. Then they resulted also using the Shapiro algorithm. If you see n equal to p into q, that means whatever in the RSA we are using, two large primes you are taking and we are going to factor it, and we are again going to apply some modulo arithmetic for that to solve this problem. So like, and this Shor's algorithm now it is breaking this RSA crypto system as well. So what like computer scientists are predicting in the upcoming years, if the quantum systems, if it is built physically, then if it is powered to inculcate the qubits, suppose if you are using 8 qubits, okay, but if you are using 256 qubits, it would need more power as well. It would need more GPU power, computational power I'm saying, and also the quantum machines has to work in a vacuum operated environment. That means with zero dust, completely sealed labs, and with high accuracy precision machines. And also the hardwired circuit should be a lot of wires needed because of the qubit scenario. Still they are doing that because still it is under practice. So there are some challenges ahead, because to implement such systems it would also go enormous cost. And but okay, anyway, we have a lot of application we have work on. So okay, then Grover 1986 he started in quadratic improvement or exponential speed up in search algorithms, and we have a lot of other quantum, like quantum cryptography and IBM quantum cloud and quantum machine learning nowadays for pricing option contracts and also for battery optimization. Like lot of advancements happening in theoretical quantum. So physical implementation, as I told, it will take some time. Still, we need some more time for implementing the complete quantum machines, because it is in the initial beginning stage. Even Google supremacy we can say, but the processor they can create, quantum processors are there. But the complete quantum hardware circuits, it is very tough to design those circuits, because the gates, whatever we are designing in the classical computing, it will not work the same way in quantum, because in classical computing we have only two inputs, zeros and one, set and reset functions. Either it is a positive voltage or negative voltage, electron flow or no electron flow. But in quantum it is 0, 1 and 0/1, that is 0 by 1. That so that it also has to think about, we have to think about like how the uncertainty principle we are locking with certain computation. So that is one of the key challenge here. That's what. Next is the complexity of the algorithms. There are different notions for measuring the performance of the particular algorithm. Suppose, say for example, Deutsch algorithm. So we have a computational complexity. Suppose measuring computation time taken by the algorithm. Sometimes, you know, this algorithm, whatever they are creating, even though it is mathematically proven, but physically testing, we need some more equipment, some more data, some more resources for solving that computational complexity. So that's called computational complexity problems. The algorithm should not take more time for its execution to execute some other program. So that is called computational complexity. Okay. So the next is space complexity, such as measuring the space memory used by the algorithm. Such as, even we know this in DSA, right? We have all studied data structures with analysis of algorithm. And DAA, there is one more course also, I think in our BTech, MTech we have studied, and also in PhD courses we are reading analysis of algorithm, where we are seeing number of different algorithms, how they perform in worst case, best case, and average case, and also there are a lot of notation, big O, like lot of other log and models and other things you are doing. So that is called space complexity. So for every algorithm, even if it is a classical computing we are measuring, then why not quantum? So quantum also having, they have to experiment and go through all these complexities. As well as in quantum, we have to look on to communication complexity. That means quantum computer also needs internet for a distributed algorithm. Suppose quantum, what is the use of quantum? Is there a lot of applications such as logistic applications, drug discovery applications, and also cryptographic applications. So it is not in only one system, it is with multiple systems, right? So that time we have to use the internet, we have to connect with lot of other machines. So that time the quantum has to be that replica, algorithm replica should be there in all the places. That time quantum machines also should be available, because even one quantum machine would cost many $1 million. So that time they cannot have, as of now in 2025 I'm saying, they are not having that many quantum machines all over the world, only simulations they are doing. So physical implementation, they have to think about the communication complexity. And the next is information complexity, like how the information is taken from one place to other place, such as we have to think about the quantum teleportation also here. Teleportation is not only the science fiction movie concept, it also can be, it is proven, but practically we can say like it is not false, but it is not true as well. That means we can do the teleportation using quantum. That means information carrying atoms. One atom is carrying information from A to B. That means it is not swapping just the information, but it is carrying information. So it is reading information with A as well as it is giving value to B. And also after the giving, the A is also holding the original information. That is like completely data integrity will be taken care in quantum computing. There is no data loss, no integrity loss. That's what it's all about. Distributed algorithms in information complexity. And also the query complexity. So how much data set or how much big databases, how much search elements you are giving, that is query complexity. So usually in a normal classical computing, we have some defined limits, otherwise the computer will hang on, system hang on will happen. But in quantum systems, we have more and more enormous power as we have like we can experience like more queries also can be solved by quantum machines. Okay, so this is how we have to understand the query complexity. Okay, so here in quantum machines, they are using a word called oracle. So assumes the existence of an oracle for a problem. So for every problem, they are going to take and consider a function, and or it's a kind of black box which provides answer to the problem. So that is called oracle. So for example, if you are solving a prime number problem or factorization problem, an oracle has been created as a function. And second, and one more finding Fibonacci number, one more oracle we have to create. Like that, it is like a method or function where we are using for solving one by one to understand how it can work. Okay, so like this. So the query complexity of algorithm, which is equal to time taken by main module plus number of calls to oracle. Okay, simply we are going to create that for dumping all the qubits into it and making the qubits to function into the gates. That is oracle. Okay. Okay. Now, as of now, if anyone have doubts, you can please ask, or else we'll continue the session, because up to that, if you understand, you can easily go for the next understandings. Any doubts as of now? Is it fine for everyone? Even you can put it in chat box, or you can raise your hands, or you can unmute. Yeah. Thank you. So clear, sir. Yeah. Okay. Thank you. So now we will proceed ahead. So like this is the examples what we are seeing here. Logarithmic computation. Suppose one oracle we are creating for solving that particular problem with an algorithm, like that linear program solver, prime factorization, like that. There are a number of different oracle is created for each and every of the problem. Okay. Yeah. Thank you, everyone. I think you're saying yes and clear. That means I'm happy, because one thing is, yeah, someone raised hand, Vijay Kalla.
Sir, can you please give the example of a qubit, sir?
Yeah, sure.
how the input we are considered?
Yeah. In the upcoming slides, I have that. I will tell you. So first, I'm defining what are the functions and how we can understand. Then I am having single qubit, multi-qubit, as well as Hadamard gates. Okay, I'll be coming in the next
sir.
slides.
Thank you, sir. Thank you.
Yeah. And one more thing, honestly speaking, is the quantum computing as well as quantum physics or quantum mechanics, we cannot completely understand, because those who completely understand, that means they did not understand anything, because quantum is highly uncertain. We are using quantum to solve the uncertainty. That means to make the process speed up, to make the solve the complex problem, like that. But understanding quantum is like understanding atomic level. Okay, so but anyway, we need to understand that. That's what we are understanding, some theory, and we are understanding some algorithms and so on. Yeah, there are some chats. Will it be general purpose or special purpose machine? Can you clearly tell what's your doubt, sir, please? Are you asking about quantum machines? Dr. Yugandhar.
Like our computer, it will be used for all the purposes, like whatever may be the software we can run. But is it
Sir,
meant for only the special purpose application you are designing for some, suppose say the weather forecasting, something like that?
Yes, sir. Yes, sir. Okay, so this quantum machines, for simulation purposes, weather forecasting, we can do it. But I am telling the examples such as logistic operations or optimization, drug discovery, this kind of weather forecasting. If it is coming to a bigger picture, larger data set, or unstructured database, we can say. So that time we have to use quantum machines. That time it will be not like a simple general purpose classical computation. We have to use a special quantum machine that also physically to be available. So that would cost very high. So that nowadays even Google or Microsoft, they're having quantum machines very limitedly, because they need to invest and they need to test in a very rigorous way, because the testing also would take some years, because the hardwiring will take more time to connect all the gates. I'll be talking about quantum circuits also today. So in the upcoming slides, we will discuss about that, sir. Is it okay? Okay. So this is how we have to understand the oracle. Okay, now how to understand the different complexities in the algorithm is, suppose the time taken by main module by number of calls to linear program solver. Suppose I'm having a linear program problem. Suppose the search algorithm, for example, I'm having number 1 to 100. So in that we have to find some number like 65 or 67 something. So that time we have to go and search every number. So it is like big O of n. Okay, so for n items. So that time if you keep on searching using the linear equations or linear algebraic equations, it would take more time. Similarly, for example, graph coloring algorithms, it is NP complete problem where it is taking exponential time in most case. That means simply to say this, suppose India have 26 states, assume, I think more than 26 states as of now we have. Suppose each and every state have one color. I want to color it in computer. Okay, in a classical computing, what it will do, it will apply one by color for 26 states. Okay, now what will happen if I want to merge the states that having a same spoken language? Suppose Telugu, like Andhra Pradesh and Telangana, both states having majority of Telugu people. So I want to color it in the same color. That time what will happen? Again, the system, that search algorithm, what it will do, it has to again go through all the states one by one, and it has to color all the states again with the same color, whichever having the same spoken language. That time it is 25 out of 26, because one color for 2 states, right? So that time again big O of n will come, because the graph coloring is one of the toughest problem in time complexity, because it is taking exponential time. But the same graph coloring, if you fetching it to the quantum machines, what will happen is it will go to 2 gates simultaneously. One is for coloring, one is for finding the language spoken. So at the same time it is doing the quantum parallelism. So it would be half time lesser than the actual time. So this quantum having, as you are increasing the number of qubits, I'll be telling what is qubit also. So as you increase the number of qubits, the power of quantum is increasing in exponential way. So the quadratic speed up will happen in this method. So that's what we have to understand what is oracle and what is the complexities of algorithm. Okay, now what is query complexity is, suppose we are saying we are giving too many queries to the machines, the machine is hang on. Suppose the classical computing, traditional computing, we are having simply, if you are searching something in Google is giving you answers within some nanoseconds, okay, right? Some microseconds it is giving 1 lakh answers. Okay, so one query, okay. What about Google don't have a backup server, a simple standalone machine, or Google don't have a cache memory? Like if it is having lot of things, then what will happen? It would take more time to solve a query. Say for example, simple. Earlier irctc.co.in, our train website, like railway reservation website, it is having a single server. That time during Tatkal booking time, every time if you are booking, your money will be debited, but ticket will not be generated and it will be waiting list, unfortunately. So that time, because of it, that multi-query handling is not there. Then they started approaching many companies, including Amazon. Then now that problem is solved because they are using the multi-tier architecture that is linked with some other companies. So now that is called multi-tenant model. Like even many queries they can able to handle with a single system. The server will be capable to handle the queries. So these kind of models are coming. Similarly, here in quantum, even with multiple query, this quantum machines has to solve all the queries side by side, and even the query complexity will be solved with each and different algorithms. That is called query complexity in quantum. Okay, so this used to prove the quantum computer is very much powerful than the classical computers. Okay, now why we are going to understand, or why we are going for these algorithms? This is the motivation to prove that quantum is best, and also to prove quantum is faster than the classical computing. How? So we need to give the inputs like what we have given in the classical machines, and also we have to calculate time where it completes and which duration it is taking the execution time to complete. So by analyzing all these things in 1992, they started working, Deutsch and Joshua working on that, and they proposed with the paper called Deutsch-Joshua algorithm. In that they clearly mentioned with mathematical proof, stating that quantum computing is better than a traditional computing with polynomial time. That means p times. That means they can complete without going to NP-hard. That's called NP-complete and NP-hard also. So this is going in polynomial time. That means, suppose, I think you know about the polynomials and things in linear algebra and in mathematics. We are also talking about the Fourier transforms. So in that, what will happen, if you keep on increasing the powers, suppose x power n, okay, so that time it has to go with power of 2. The 2 power n minus 1 queries plus 1 it has to solve. So that's what they are telling in quantum, how much efficient it is to work. So Deutsch and Joshua created those mathematical proof to solve those classical for finding constant or balanced operations. Okay, so this is the problem statement. So the oracle or black box access to a function f. Okay, so say for example, a normal, you can assume any functions. Okay, prime number finding functions, whatever. Okay, so the input is n bits here, output a single bit. But here the problem is it may be either 0 or 1, or 0 or 1, or 1 or 0. So here we have to understand with one example. So what is the famous example for all the probabilistic values? Tossing a coin, right? So usually a coin, okay, I'm sorry, I'm able to write here. Anyway, I will try to visualize this. Okay, one coin is having head, the same coin is having tail. Okay, so this is the coin. Assume this is the coin having head and tail. Okay, so this coin, while if you are tossing from your hand, okay, it's going up, right? So the moment it is tossed from your hand, and again it is coming down to ground due to gravity. Okay, so here one state, here one state. Now here, before tossing it is head, for example. After tossing it is falling down with tail. Now we know the probability of this, right? 50%, so 1 by 2, right? Everyone knows this. But quantum is telling all about what is the probability here. That is in the air. What is the probability of the coin? It is what quantum computing and qubit is all about. So can anyone answer for this? What is the probability of the coin in air? That is, it is keep on flipping in the air. That time it will be head, sometime it will be tail, sometime, but still it is not reaching the ground. So what is the probability of finding probability of that coin that is in the air? Okay, so that we cannot find. So that this bit is either 0 or 1 or 0 or 1. So this is how we have to understand the qubit. Okay, simply here the probability depends upon, it is not number of times it is flipping, but how much number of times it is nearing to the head. How much number of times it is nearing to the tail is the probability of the coin that is in the air. That means, suppose, say for example, in classical way, if I am solving this equation, suppose it is x-axis, okay, and it is y-axis. So I'm having here 0, okay, here it is 1. So now what is the value here? That is on straight line. Okay, now this is, say for example, 45-degree inclination. I have drawn a line with 45-degree inclination. I'm not using my pen, I'm using my mouse to write this, so my handwriting is somewhat poor. Please adjust. Okay, now, okay, so what quantum is telling is, whenever we are approaching from 0 to 1, from this way to this way, it is called quantum rotation. Okay, whenever this line is now, it is keep on approaching to 1. Okay, now whenever the line is here, now we have to calculate distance of this distance. See, I will change the pointer color so that you will understand it better. So the color between this and this. Okay, now say here this, okay, this green color line, it is near to 0 or near to 1? It is near to 1, right? So that time this will be 1 only. This line value will be 1. So here the 45-degree, it will be 0 or 1. We cannot say anything. But see, when I will change to blue now. Okay, now see here, if the line is here, that time the probability will be high for 0. That is, it may be 0.85. Okay, it may be 0.35. But always it will be lies between 0 to 1. It's all about the quantum rotation. So when coming to here, this problem, the H and T, okay, the head and tail, in the air, whenever it is nearing to head, that the probability of head will be higher. Whenever it is nearing to tail, the probability of tail will be higher. Like that, the quantum qubit is designed. Hope now you understand the qubit. Okay, but still we cannot understand it completely because we cannot predict and we cannot say certain value of 0 and 1 in air, because we are thinking in classical way, because coin is classical, we are physical humans, we are classical. Then how we can visualize the quantum? Now if we become subatomic or if we are a particle, then we can understand quantum. So that in most of the science fiction movies such as Quantum Mania, there was a movie by Marvel, right? So even that time they are telling, if you want to understand quantum, you want to go into the subatomic world. There is one sci-fi movie. Okay, that is a different scenario, but okay, anyway, that's what I want to insist here about the quantum. Okay, now completely how to understand quantum is, okay, I will open the slides. Okay, now we will see. Yeah, so we have to finally find the f of x is either constant or balanced, because the Deutsch algorithm is telling why we are finding constant balances. If it is constant, then every inputs become 0. That means every input and every output should be the 0. That means if it is constant. For balance means even one change in one bit also, that means it is in balance. That means the classical computing failing in some operations, but quantum computing is very fast in those operations. So our aim in Deutsch algorithm is to find whether f is constant or balanced. We'll see now one by one how to solve this. Okay, now in classical, we are giving input functions, we are giving input values to a function, and we are getting some outputs. Okay, so n bit input, n bit output, and for 1 bit input we are going to make the XOR of that function f of x, then we are getting a 1-bit output. Similarly, in qubits, in quantum, what we are doing, n qubit input, we are going to give n qubit output, and 1 qubit input, we are going to get that y XOR with f of x, and 1 qubit output we are going to get. But here the problem is this qubit, this 1 qubit may be 1 or maybe 0. It is not same like classical computing. Why? Because say for example in AND gate, AND gate, what happening? We know the outcome. Whenever a number is multiplied with 0, it is 0. Whenever 1 into 1, 1. Okay, fine. So in most of the cases in zeros and ones, 0, 0, 0, 0, 1, 0, 1, 0, 0, but 1, 1 is 1. But it is not working in quantum because 0, 0 sometimes 1 and 0, 0 sometimes 0 also. So how to predict this and how to evaluate this is, first we need to understand which side of qubit you are going to visualize in your output. So that prediction is available, then only we can understand this qubit. So that prediction who will do, that gates will do. Which gates? The designed hardware gates for that particular algorithm will do. Okay, so what kind of design it is, we'll see. Okay, so it need to find the correct answer always, because we should not, in quantum we should not go for a wrong answer, or we cannot say a near accuracy answer. Always it has to say the correct answer. Okay, so must query more than half of input space and no optimization possible to get the answer correctly always. Why? Because again one more problem I want to say here. If you want to there are 100 doors, okay, like there are 100 doors and it is locked. Okay, 100 rooms, that is locked with some 100 doors. Okay, so same room, same doors, it is locked 1 to 100. And the problem here is, I will use, okay, in some room, okay, even I don't know which room it is, there is one apple, red color apple is there. Okay, but we don't know which room has that apple. So that time what we will do, we have to search 1, 2, 3 like that in classical method I'm saying. So there is 100th room. So what we have to do, if we have to open every door, okay, up to 100, so we have to waste the time here. So 1 to 100 we have to take one by one room, we have to open, check. Even if you do the random algorithm, random search algorithm also, we need to find it. In random, it won't work always, but there is again a probability you may get in the first room itself, but the probability is very less for that. But what quantum is doing here, initially, rather than going to all the rooms, the first step is it will open all the rooms in the first shot only. There is one method that is called C-NOT gate, controlled NOT gate. It will open all the room, and parallelly what it will do, it will see which room has that object like apple. Okay, immediately that room number is given in the probabilistic value. It will first decrease the probabilistic value, that is called amplitude amplification method. I will tell you later in Grover's method. Okay, so what happens is it will make that object value lesser than the actual value. Suppose if you are having a values like this 1, 2, 3 like that, your number of rooms, that value will be lesser. Okay, and after that it will increase all the values to exponentially. That time it will be doubled. So next time what will happen, this particular value will be high. That means this is the original value what we are expecting. This is how the quantum qubits are working. Yeah, so I think up to now hope everyone understood, right? Okay, now we will go for the DJ problem, how it is actually solved in polynomial time. Okay, now I'll explain what is qubit and how single qubit work with gates, and also how multiple qubits, and also how operation of C0 and so on. Okay, now suppose the classical NOT gate will work in different way, but quantum NOT gate especially, what it will do is it converts zeros to 1 and ones to zeros, vice versa. Okay, suppose this operation is called psi. Suppose I think yesterday I think you were clearly told about what is bra notation, what is ket notation, how to evaluate qubit, how to understand the bra and ket notation, and how to evaluate ket with tensors. I think hope you had a good discussion, right? You know about these notations? Yeah, yes. So hope everyone knows about this notation. Then it's easy for me to explain this. So now alpha ket of 0, beta ket of 1, it is going to naught. That is quantum naught. So what's happening? So psi dash is coming. So it is giving 1 and 0. So the representation matrix, we have to, it is not again a normal matrix. In normal matrix, what will happen? You know, suppose say for example matrix multiplication if I take, what will happen? Suppose 0 1 1 0 means we have to first go with rows, then columns. Again row with row. But here that is not. It is a tensor multiplication. Even in matrix multiplication, if the rows and columns are not equal, immediately we have to find an error that matrix multiplication is not possible. But here in quantum, that is not the case. Even though the rows and columns are different, also we can use with tensors. Just we are going to take the value and apply it on other bits. Okay, so that we are going to get the result of 1 by root 2 into 1 1 1 minus 1 in the Hadamard gate. So we are going with quantum qubit computation, right? So we need to work with this only. Okay, so we are getting beta and alpha here, and also some of probabilities output states we have to have this into 1, because again here why we are taking into this value into 1 is, again I want to tell you about photonics and come back here. What is the magnitude and what is the force we need to understand here? Suppose you know the famous equation, force equal to mass into acceleration. I think you know this, right? In physics, in classical physics, force equal to mass into acceleration, right? For F equal to ma. It is one of the famous scientists long back it told. Okay, suppose I'm having a pen here. If some external force is applied, this displacement is happening. The pen will be here because of the force applied. The pen is moved from here to here. But if the same pen, okay, we are hanging in a thread, the same force is applied. The pen is not moved from here to here, but rather it is rotating circle wise and it is coming to the same place. Now here it is called T, like torque equal to I into alpha, right? Am I right? Those who are physicists, you better know, you would have studied this, and also even every computer science graduate scientist, we know about this. So here what happening is, it is not only about the magnitude but also about the torque. Okay, so this torque, what happens? The object is in rotation. That means it is having some other force. External force is applied, same force value, but in some other direction. So it is some other dimension as well. So suppose in classical things we are having a graph x and y, but in quantum we are having one more line, right? I told, say for example it is z dimension. Similarly here it is one more dimension called rotational dimension. That is coming in quantum parallelism. That means the magnitude of alpha square plus magnitude of beta square should be 1. That means the probabilistic value combinedly form the value of either 0 or 1. So that is the output state. So that in unitary matrix we are having the values with not certain but uncertain to certain. Okay, so that this formula is applied. This is similar for even why the electrons are revolving around nucleus. If the, suppose there is called electron bending also, like how it is bending because of the quantum mechanics and quantum physics, because from one metal to another metal, why it is going, because of transmission, like lot of things are discussed in physics. The same concept we are going to take and we are going to implement that in computers. Okay, and any unitary matrix, yeah, so we are going to play with the specified quantum gate. Okay, now this is multiple qubit quantum gates. Now I'm going to explain what is control NOT gate. Suppose already we have taken 1 qubit. Now see here the 2 qubits are there. I'm taking a pen, I'm writing here. See here 0 0 is there, output is 0 0, because again I'm saying it is not working similarly like what we are having a NOT gate in our classical computing because it is controlled NOT gate. That means 2 qubit as input and outputs are 2 qubits. And action is, if the control qubit is cut off 0, then target would be unchanged. If control qubit is cut off 1, then target would be flipped. That means it will be changed to 0. If it is 1, then 0. If it is 0, then it is 1. But how we can identify this? This is the overall idea behind that. See here, we are going to do the addition mono or XOR also we can say. Yeah, XOR gate. Okay, so the control as well as the target. Here also there is no one output but 2 outputs. Okay, usually in classical we have only one output, but here it's 2 output. Why? Because there is called controlled output as well as target output. That is 0 0, it will be 0 0, and 0 1, it will be 0 1. For 1 0, it will be 1 1. Usually it will be 0 1, but here it is control output will be 1 as well as target output will be 1. And for 1 1, it is 1 and 0. So by this method we have to understand why this is happening for the quantum bits. Because in control NOT gate, if the control qubit, because this is control qubit, okay, 0 0 1 1, then it will be unchanged. And if the control qubit is 1, cut off 1, okay, so these gates, then the target would be flipped. Okay, because even the target qubit, if you see, it is 0 1, so it will be 1 0. Okay, so this is how happening in the multi-qubit quantum gates. How to represent this in matrix or any other symbolic representation is, so say for example, here I want to say one more thing here is, so suppose A is having one value and it is keep on traveling, and in one point of time A want to give the information to B. Okay, so that's what here they are tapping the information and giving to the other variable. Suppose example I'm saying, okay, in physics, what will happen? Yeah, some sounds coming. Yes, any doubts? I think someone unmuted mic. Can you please mute your mics? Yeah, thank you. Yeah, so what I was saying is, so here the particle is traveling from one place to another place, and it is going to transmit it information to another variable or another level. Suppose there is a ground state for electron, okay, and it is excited state, okay. So there is called pump state where the electron is flowing from one place to another, ground state to excited states, okay. So in the middle, what they will do, they have to transfer that data. So in computation, it is in physics, but when coming to computation, what is happening? So this ket of A, it is carrying some information. We have to understand the quantum teleportation here. That particle is going to give that value with B. So the A is here, B value is also here, and also A value is retained in the end of transmission. That means A is XORed with B. B also here, A also here. So that quantum is reversible in nature. We can also backtrack and go to the input again. But in classical computing, we cannot do that. For example, in AND gate, we are having 0 and 1. Okay, I am giving example 0 and 1. It is going through AND gate. I think you know about AND and OR gate, right? AND symbol is like this. So what is the output? Can anyone say?
0.
Very good, 0. I think immediately Mr. Vijay told, I think, thank you. So it is 0. Okay, 0. Fine. Now I am removing this 0 and 1 here. Okay. Now I am removing this output also. It is AND gate, that only you know. Okay. Now I am giving output as 0. Can you say exactly say within only one option, what is my input?
Either 0 and 1.
No, I want only one answer. Exactly. So in classical computing, it is the problem. We cannot reverse it, right? Now, are you understanding this? Because we cannot do the reverse process. In So we are missing the input. We are losing the input. After the output we arrived, it is very tough to predict exactly, because in AND gate there are three possibilities. It may be 1 0, or it may be 0 1, or it may be 0 0, right? There are three possibilities to get the output as 0. Am I right? So that time the exact reversing is not possible, but in quantum it is possible using that Hadamard gates. So that's what I'm saying. So this unitary configuration and matrix representation, why we are studying is the matrices, whatever we are getting, to visualize the multi. If you are saying multi qubits, it means more than one qubit. It may be 2 or 3 or more, but it is called multi qubits. But what is the use of multi qubits? Multi qubits are essential to perform the entanglement. Again, I think you know about entanglement, right? Entanglement means more qubits are attaching together to perform the operation in a better way, in a parallel way. Okay, we can say it's a parallel way. And also, I think you know about superposition, right? I think I explained you here. Yeah, this is superposition. The coin that is in space, right? This is called superposition. We cannot predict the value exactly, but we can assume the value. If it is nearer to 0, it is 0. Nearer to 1, it is, I think, the probability value. Suppose this value, this 0 value will not be 0, but there is more chance, that is 0.85% chance. That is 85% chance for the coin to be, maybe if you are thinking it is head and tail, that to be head. Okay, so 85% chance is there. So 0.15% chance for this, because the line is very nearer to this. So that is what we have to understand, the third dimension in quantum. Okay, so that's what I am discussing here. Okay, so here that is what we are getting these values as a whole value, and we are going to get the ket value of everything as a reversible gates. See the values here also. UCN, again the original values we are retaining, but it is only representation of matrix. But here, how the Hadamard gate reversing the gates, that I will tell you. See here, the reversibility of quantum gate, this is what I am telling. See here, the gates we are applying in Hadamard of H, ket of 0. Here it is 0, right? Finally, again we are going to yield 0 only. In between we have some output. Again we are processing it, the output with Hadamard gates, we will get the initial input. So we are not losing the input in quantum. So this is one of the speciality in quantum. We can proudly say, every participants, please listen. So if someone asking you, you attended the quantum computing workshop or whatever, FDPs, what you learn, you can say about this reversibility, they will be surprised. Because you can say, that if you apply double action, that means 2 times if you apply the Hadamard gate, then you will get the original result. That means input you will get again. In classical, it is not at all possible, right? So just now I told 0 1 if you are giving an AND gate, we cannot predict again what is the, after getting the output, we cannot predict the original input. But in here in quantum, in double action of Hadamard, we can get the original value. So why I'm discussing this is the algorithm that is designed by Deutsch. This Hadamard gates designed by Deutsch to show the world that quantum is powerful than the normal classical machines, because we are going to regenerate the input by using the output. Okay, this logic you can say. Okay, now how Hadamard gate is designed is, I already told you about the rotation, quantum rotation. The similar way we have to understand this. It rotates the ket 0 vector about x-axis in clockwise by 45 degrees. Suppose 1 by root 2, 1 1 1 minus 1, tensor of 1 0 will yield 1 by root 2 of 1 1. That means if you are going in 45 degrees from here to here, ket of 0. Okay, so then the value will be 1 by root 2 1 1. Okay, then rotates ket of 1 vector about x-axis in counterclockwise direction by 45 degree. Again what will happen? You will again get the original value. Suppose, how to understand this is, simply if you reduce that into binary, it would yield 1/2. If you reduce it to decimal, it will yield 0.5. Okay, that means exactly it may be 1 or it may be 0, not 1 0. So this Hadamard gate is mainly used for Deutsch algorithm as well as Grover algorithm to solve the complex problem because of this functionality. Okay, so any single qubit gate could be decomposed into product of rotational matrices together with global phase shift. There is also called phase back, that I will tell you, phase kickback. That also similarly we have to understand like this. So now how it works is, step 0 is input we are giving 0 and input functions, and also ket of 1 we are giving. Now yeah, Hadamard transform, how it is getting transformed is, so we know Hadamard ket of 0, we are going to apply this tensor to form this, and we are going to evaluate either it is 0 or 1. Okay, so this is very simple to understand. Now step by step we will go. Now in h ket of 0, what is happening? 1/√2 ket of 0 plus ket of 1. Why we are doing this is, I will tell you simply. First I will tell about the classical gates, then we'll come to quantum gates. So now, if in classical what is happening, it is 0. I am taking to tell, if you speak, it is maybe plus 9 volt, right? Because it is in peak, it is high. It is 0. That means, but if there is one more square wave here, okay, I am going to take this is minus 9 volt or minus 10 volt, whatever. Okay, so this is how we are understanding the classical way of understanding the electron flow, or simply even a sine wave, square wave, or even whichever way we are understanding. This is the way we are understood and we are processing that. But in quantum, what is happening? We are not going to design the same way what the classical computation or classical physics works. Here, one way will be like this, one square wave will be like this. Suppose next square wave will be very much more, but even though it is one peak and this is higher peak, but both are taken as the same values. Only the suspected peak that is in different dimension, this will be taken as the end result. This is called amplitude amplification in quantum. That's what they are doing here. In ket of 0, it is coming 0 and 1. In ket of 1 and Hadamard, we are having minus values. And finally, this transform evaluating the functions, that is ket of A is defined as 1/√2 power n with all the values of 0 to 1 up to the n numbers with this value, and we are going to input here. See, and one more thing is here, not only 0 or 1, multiple bits of zeros, multiple qubits. That means we are adding, suppose example I will tell you. So here we are deploying only 1 qubit into this particular Hadamard functions. So we are getting this. Now if we are supplying, suppose two qubits, suppose 0 0, I'm going to give 0 0 ket off, and we are going to, here also we are going to evaluate that. Then here what will happen is, in place of x, we are going to have 1 0 ket. Like again, 2 answers will come. The same ways we have to understand for multiple qubits. It may be 0 1 or 0 1, whatever. We are going to get that many qubits in your output also. And again I'm saying it will be same or it will be different, or it is 100% same, it is not at all 100% same. So it is depending upon the functions what you are inputting through an oracle. Oracle, I already told you, it's a black box for defining that function near to the probabilistic values. So that's what happening in the Hadamard transforms. So this is what I told in phase kickback. We are deploying 2, that is double Hadamard. I told you, right? What will happen in double Hadamard? we can retain the inputs. That's what happening here. Okay, we are going to retain the inputs, whatever we are giving in double Hadamard with C0, control not functions, we are going to retain. And this is how we are evaluating step by step. C0 of ket of x and y, which is ket of x, y plus x. So again, finally, we are rewriting with the functions with the value like this. Step 3 is, yeah, so this is the final value. Any doubts? Someone is asking. I request all the audience to mute. Whenever you have queries, you can unmute your mic. So here the Hadamard transform is clear. There are some disturbances. Yeah. Can you please mute your mic? This NV Lakshmi is coming. Okay, we will continue this. So it is rewritten as 1 by 2 power n. Yeah. So with summation of, so y value we are finding because we need to find the y whether it is balanced or constant. So can you everyone please mute your mic, or I request moderator admin to mute all the mics except me. Okay, so I muted it. Now, if you want, you can unmute it anytime. Okay. So now why we are finding this is, we need to find whether the y is balanced or constant. Suppose after this evaluation, what will happen is that f of x, this y value, after calculation f of x and x into y, what will happen? This y value should be 0, all zeros. Even if 1 coming inside this qubit, then that means it is balanced, it is not constant. So we are the final outcome for our Hadamard transform is to find whether we are calculating the y value is coming zeros or any ones. Okay, now what is this happens is, first Hadamard we applied, then a function we applied, then again double Hadamard for reversible process. Now what is this? Anyone can say? So I told about the rotational quantum, right? That's what happening here. So the line is initially here and we are rotating to 40 degree or here. So the probabilistic value will be calculated at the end of the function to reverse the inputs. Okay, so that's what happening here. Okay, so
The student's measurement, sir.
hello, yes.
That symbol, last symbol represented a measurement, sir.
Yeah, measurement. That's what. If measurement output is all zeros, then f is constant. So we are going to find, our goal is to find the measurement, whether f is constant or f is balanced. So suppose, you know, if 1 comes also, that f is going to be balanced. So here what is happening, this measurement, this output value, how we are finding is, suppose I told you, right? So this values, which probability it is nearer to, that's how we are making. So see, if measurement output is all zeros, f is constant. If for any other output, f is balanced. Okay, so this is how measure the first n qubits. So this is how the Deutsch and Joshua initially mentioned, and this concept is used in Grover for explaining the unstructured data search algorithm. Let's see that. What is Grover's unsearched? So there are number of search algorithms are there and search methods are there in classical. In quantum, Grover's in 1994, he found out that, and 1996 he published it, and after that, many companies started buying that algorithm and using in their system. So, say for example, that is United Parcel Service and FedEx companies, they are using this Grover's algorithm for their pathfinding, efficient pathfinding through multiple destinations. And also machine learning classification algorithms that work with Grover's model can do better. Okay. Okay, and one-way functions. See, one-way function, example, hash function also, it is hard to calculate but easy to verify because even hash is used for verification. Even Google password, right? Your Google password also saved as hash values, not directly your password values in the Google server. Hope you know that, because hash function is one way and also it is powerful. Okay, but it is hard to calculate because it is having number of I think secure hash algorithm, you know, right? 512-bit SHA. So there's SHA-1 and SHA-2 algorithm. There you can find it. For example, Sudoku, factoring large prime numbers, optimizing school bus. So these are all some of the examples. We can solve it very easily using quantum approach because it will take more time for the machine to calculate these values. But the quantum machines can do it within some seconds. Okay, the best example is the brute force attack that is happening nowadays in many password guessing attack. So that can be easily can be guessed through quantum machines. So Grover given an algorithm that given a space for the hackers to do that, but the hackers are lack of that machine. If they have the heavy quantum machine, if they know the Grover algorithm how to implement it, then done. All the banking systems will be compromised. Okay, so what Grover is telling is, suppose the search problem is there. Suppose we are having a random number between 1 to 100. So you are going to pick a number. Okay, suppose you are taking a number like 10 or 12. So we have to go through first all the numbers for searching where the 10 is. Suppose if we are storing an array index of A0 to A99. So we need to do it for 100 times, right? So because we don't know where the element is found, because we need to go with, even we have lot of different searching techniques, linear search, binary search tree, DFS, BFS. We have lots of search, A-star search in AA, but still it will take some time to search all the elements through an array. So the worst case, it requires 99 calls to the classical oracle. But here the quantum, it is the size of big O of root n. But why? I will tell you why. Because this is yeah, again, see here there are sorting procedure still require time. Searching, okay, but again sorting will take more time. Okay, so for that, if you go for quantum based searching, it is even not even half, it is in quarter we can complete. That means if we take 100 seconds for this classical search, okay, it is taking only 25 seconds. Okay, 1/4 we can complete in quantum. But I am saying for a normal, but Grover's algorithm working in nanoseconds, not even microseconds. It is very fast. I am saying 100 seconds in a, for example, but 100 microseconds or 100 nanoseconds if a classical computer takes. Grover's algorithm, if you apply on quantum, it will take only 10 microseconds or 10 nanoseconds, like that. Okay, so now who is Grover, why he invented, and what is the purpose of invention, I will tell you now. So in 1996, Love Grover, he created this Grover's algorithm. Okay, he is Grover on that time. Now he is old. Anyway, he is one of the biggest scientists, computer scientists. He created this algorithm. So it can be solved using quantum machines and also by classical machine, but the classical machine will take more time. But what is the power of the Grover's algorithm is, after Shor's algorithm, he created this algorithm. So this Grover's algorithm, if it is given into the quantum machines, it would break the RSA security. Already some Chinese proven that, but still they have used only 8 qubits for that. But if you are using more and more number of qubits, then easily it can be 256 qubits we are using in banking systems now. Some banks are using 512 bits also. 512 bits of encryption. Okay, suppose in future 512 qubits coming and sorting out this algorithm, then that's it. So like there are some in future it may come, but not immediately. Maybe 1 year or maybe 100 years, we don't know. But quantum is on developing stage. Okay, see the vast difference, exponential difference here. In normal, it is taking unstructured database, it is taking big O of n, but here big O of root n. That means from here we are jumping to here. So we are decreasing the time very, like, see here, example, choosing a randomly by 1 to 100, 99 attempts. So in classical, root of 100 is 10 circuit. That means if you need 100 nanoseconds, it needs only 10 nanoseconds. I told, right? Similarly, and also what is quadratic speedup is, if you are applying the root, that means it will exponentially we are reducing it. Okay, so it's called quadratic speedup. Suppose if we need 100 wires in classical, in a hardware, we need 10 wires in quantum. Hardware circuits such as, I think you know, breadboard design, for that time we were doing in EC, or computer science students also know. For simply lighting an LED, we have to do number of wires connections in a breadboard, and finally in one of the output we are placing the diode to glow, right? LED to glow. Similarly, we need that much circuits for a quantum machines to operate. So this is the power of the quantum's Grover's algorithm. Okay, now how to understand this Grover's algorithm is, the first method is amplitude amplification. Hope I told this amplitude amplification is starting, right? So how to understand immediately this balance superposition and new state with 1 get amplified is, I will directly tell you an example. Okay, in a police station, okay, there are 5 members, they are standing. In that, in this 1, 2, 3, 4, 5, there is one member is a thief. A police personnel is there. He want to find who is thief. Okay. So what he will do? Usually, this policeman, he is a policeman. In this, yeah, tell me.
அதை ஸ்டாப் பண்ண முடியலன்ற சவுண்டா கேக்குதுன்றீங்கல்ல, அதுக்கு சொல்றேன்.
Hello. I think you unmuted someone.
சரி.
Yeah, I muted everyone now. You please raise your hand, then I will request for, you can request for like, because we are in middle of the algorithm. Again, if someone is talking, we are missing the flow actually. Anyway, let us see. So then how the this police example, thief example, how the police usually will not identify everyone as thief, but he will suspect someone. Okay, the suspicious guy, he can be a thief, but not 100%. So they will put him aside, they will inquire him later. But all the others are less suspicious than the first middle one. Okay, so what they will do, so for them the probability is somewhat lesser than this suspected guy. Okay, suspicious. Even in cyber security also, in cyber crime, cyber criminals, the evidence will play an important part. Anyway, in that the suspicious thing, they will take evidence and they will go work on the IP addresses and all, right? So like that, the suspected thief will be given more value and they will be putting in the negative values. Okay, so what happens, it will be in the downside now. All others will be in the up only, all the 4 items, 4 thief, okay, 4 normal persons. Okay, so the suspected person, this, see here, increases probability amplitude associated with the answer. So the suspected is the answer. We are going to, the quantum machines will take that qubit for the suspected answer, because the nearest probability, according to this value I told, right, nearest probability value near to that 0 or 1. So that is the suspected one. Okay, then decreases all their probability amplitude. So other things they will decrease. Now the balance superposition will be 1/2 of 0, 0, 1/2 of 1, 0, 1, 1, 0, and 1, 1. All the superpositions we are taking, because it may be 0 or 0 or 0 or 1 like that. The new state with amplified is this particular suspected or we cannot use suspected, we can say it is amplitude, increased amplitude. Okay, this will be higher in the next time in the double. Suppose initially it will be 50%, now 50% more will be filled with the existing amplitude. So that time 50 plus 50, the probability will be 1, ket of 1. That time it will be the answer. So this is how this amplitude amplification works. Okay, now see here, that's what the same definition. Start the balance superposition and assign a pace of -1 to the chosen ket. Okay, and they are reducing the value to negative value. Again they are increasing in the next level to the double value, so that it will be the final answer. Okay, so now we can easily understand this is the over answer. But how this chosen ket works is because of Hadamard gate, like this. See, 1 1 goes to 1. See here, this will be going to here. All others will be not be having these values. There is no value here, no value here, no value. Only this is having the answers. So this is how the Grover's algorithm works. Now we'll see the implementation circuit. See, here there are two parts. One is called the Oracle flips. Before that you see the original Hadamard gate, actual Hadamard gate. First all the qubits has to go with this. Just now I told in Deutsch algorithm what is Hadamard, what is Hadamard transform, what is quantum Fourier transform for the Hadamard, right? So that Hadamard gate, after it goes to the two important component, one is called Oracle flips, the sign of the desired search element. How it flips? Like this. It flips. So the sign is here positive, see here it is negative. Similarly, here it is positive, but it is completely on negative side. So that Oracle will decide which has to be flipped the sign. Okay, like this. So this gate is important for flipping the sign of the desired search element. Okay, and second, that's called diffusion operator, inverse amplitude about the mean. Okay, now what is mean? I think you know about the average, mean, median, mode, and other thing in statistics and data science, right? Similarly, here they are going to calculate the mean, and they are going to increase the value for this particular desired output, and all others will not be increased. They will decrease. So it will be going to 0 or either negative value, but it is only going to 1. So this will be finally selected. This is how Grover designed this matrix and algorithm. And again, finally, we are going to find the balanced and constant function, the measurement value, and the measurement, if it is 1, that will be the final result for that particular ket of 1. And this will be selected as the desired output. Okay. Okay, now overall, in a classical way, if we are thinking how we are finding the search methods, or see, we have to repeat again. I am saying it is not only one time, it is repeating the root n times. That means if it is 100, then if it is to over 100 values coming here, then 10 times you have to repeat this amplitude amplification, 2 parts simultaneously. Then only we can get the desired output. Okay, so now I think you clear. Again I am writing. Now there is first Hadamard gate, right? Yeah, sure. Please diffusion operator. Okay, fine. Again I am see here. Again I am explaining. Please listen. I think hope you understood this. Amplitude amplification. Mr. Sanju Chauhan. Okay, fine. So what is amplitude amplification is, suppose if the desired or the, suppose if you are going to, because the quantum gates, what they will do, first I will go to this Hadamard. Yeah. Here what they are going to do, this Hadamard gate in transform, that's called pace kickback. So after passing this step 1, what will happen? The input itself, suppose there is only 1 and 2. But if it is multi-qubit, here also multi-qubit, like that there are more number of lines are there and more number of Hadamard gates are designed. Then what happened? So then more number of outputs also, qubits also will be generated in the next step. But before that, here only we are going to sort out and evaluate this function. Up to 0 to 1, it is the whole set of n, because the x belongs to all the values. So what we are doing is, we are going to, the quantum is going to find the exact desired value. It's going to verify the value here, that's it. Because they are going to apply 2 Hadamard gate in Grover's algorithm. Here we are just understanding Hadamard transform. See here. We are understanding Hadamard transforms. We are not applying Hadamard gate. But see here, if we apply 2 Hadamard gates in Grover's algorithm, we are going to get the answer. Yeah, that's what. The amplitude amplification. So what happening here is, this is the chosen one. That means the quantum already selected one nearest the probabilistic value output. Okay, quantum doesn't make mistakes. It will, suppose if it is selecting one value that is nearest to, I'm expecting 1 is my final answer. It is selecting 0.9. Okay. One of the element have 0.9 as a probabilistic value. It is selecting that. Quantum is selecting that, and quantum is 100% sure that all the other element is less than 0.9, the probabilistic value. So quantum already selected this. So now quantum, how it is proving to the human is, this 0.9 now given us negative value, that is minus 0.9. Okay, and it is kept aside in the lower level, like this. Okay, now next step what it is doing, it is inverting all the probability. That means already it is lesser, right? Now inverting means whichever very lesser, that will be very high in the next step, next iteration. It will be very high that time. So that time the quantum easily tells you that this is the desired output I chosen, and that is the correct output you are expecting. Then the user is very silent. He don't have any words, because it is working with amplitude amplification. Okay, that's what. Okay, but what is your doubt is, okay, diffusion operator. Okay, so after amplitude application, coming to here, okay, there are 2 parts in Grover's algorithm. One is called oracle flips. What it is flipping? Here I'm flipping, right? 0.92 minus 0.9. It is called flipping. This is done by oracle. Okay. Now, what is the next step? Diffusion operator. What it is doing? Inverts amplitude. What is inversion? Minus 0.92 again plus some value very higher. Inverse amplitude. This time it will be minus 0.92 plus 0.9. But all others that time will be very less. See here. It is only correct. All the others will be very lesser. So whatever the quantum selected is the correct desired output. Hope now you got this right. Mr. Sanju, did you understand diffusion operator now? Okay. Okay, so like that the diffusion operator, okay, like that not only one time, please understand, if it is single qubit, that also repeat root n times for n number of values. If it is multi-qubit, again according to the multi-qubit values and the multi-qubit output values, and also repeat root n for the n times. That is understanding. This oracle and diffusion operator we have to perform. Suppose say for example, in single qubit, if 100 is there here, 100 input we are giving, then root 100 is 10. Okay, root 100 is 10. So 10 times you have to repeat this step. I think you know about AES, DS, right? In that AES, for example, DS, if you take data encryption standard, there is 64-bit plain text is coming, 64-bit cybertext we are generating. But there are 8 rounds, right? I think so. in cryptography. So like that, number of rounds, if they are increasing, they are going to find a very strong cipher like that. So here we have to repeat that root 10 times to find that exact answer. Okay, so this is diffusion operator. Next, like overall idea about how to do this. So develop a classical function f of x that outlines search criteria. We have to give some numbers and find an input x that's a factor of 25, like that. We can do with lot of things, but what is the final solution we are going to find? If all 0, that means it doesn't satisfy criteria. If 1, if x input satisfies the criteria. So that is how we are designing the Grover circuit. It's called Grover search circuit. See here, it is written like this, Grover search circuit. And we can create a reversible circuit. How? If you are using 2 Hadamard gates, double Hadamard, then we can also find what is the input as well. Okay, that is how they have designed this. And reversible circuit generators help create quantum circuits from classical computation. Add an additional ancilla with negative phase that introduces phase kickback. I think ancilla means ancillary. Okay, x means x dash and other higher component of x. And this is the overall 5 steps for understanding the Grover search mechanics. What are they? Let's see one by one. The first step is identify your search problem and the data, n items you wish to search. Suppose if you have 500 or 5,000, sometimes 5 lakhs, 50 lakhs components you want to search. Then what is the second step is find the smallest number n that satisfy the given number of items less than or equal to 2 power n. We have to fix one value. In that we have to find the smallest number n that satisfies these conditions. Suppose for example, I am taking only 10. Okay, I want to, that n is 10, capital N is 10. So I want to fix a number, find the number n. Suppose my search element would be 2, suppose. Then what is 2 power 2? It is 4. Okay, so now n is, the big N is less than or equal to 2 power small n. Then it is not working out, because 4 is now lesser, this is bigger. Now we have to find the smallest number n that satisfies n is less than or equal to 2 power n. So the input x represented with n bits, n qubits, because this small number n is n qubits. The superposition via Hadamard allows us to look at all values at once. Okay, again, what is superposition? I already explained you, right? Either it is 0 or 1. Superposition. It will be like a, flipping the coin. I told the example. The superposition in the air. It may be 0 or it may be 1. It may be head or it may be tail also. We cannot predict it. Okay. Now again, to find the smallest number, we can take 6. Okay. Now what is 2 power 6? 2 into 2 into 2, like that. If you keep on calculating, it will be more than 10. So that 6 we have to take. That means again we have to construct an oracle F and a gate matrix UF that flips the sign of the object of the search. Okay, so we have taken 6 and it will be minus 6, because that's the first step. After going through this Hadamard, the first step is UF, and run UF that flips the sign object search followed by U of pi, that circuit that inverts around them the mean. Suppose the mean already we are calculating. So suppose 10 items, 1 plus 2 plus 3 plus 3, like that, keep on calculating up to 10 divided by 10. So average you are finding, and mean is, we have to take a middle number and we have to find a mean. Middle number we can go in probabilistic value, means we can go in 0 to 1, but that also we can take. So this is how the Grover diffusion works. This is called Grover diffusion operator, and we have to repeat this for a root of 10 times, because we have only 10 we have taken as big N. Okay, so that many times if you rotate, what will happen? We are going to get the original value. So that's how this process is happening more number of times. If you are calculating more number of times, what will happen is that that will give the exact value of what you are searching actually. Because suppose this root of 10 maybe 3 point something, but what is happening here is we are fixing at 6, right? We have taken a small n, that is 6. If we are reversing, it will be plus 6. But in the Hadamard gate, we don't know how many elements it is getting selected using qubits, because till now we define only 6 qubits. Accordingly, we have to input that 6 qubits here and 2 times Hadamard gate, and with 1 oracle and 1 with Grover diffusion operator. That time it may go for 6 probabilistic value is more than 0.5, even 0.5. Suppose if all the elements are 0.3 and 0.4, only 6 is 0.5, it will select this one. Whenever there is nearer to 1, that will be selected. Okay, that will be taken as the overall value of the output. Then measure and read of the state with an encoding that corresponds desired item in the database, and finally map the resulting state back to the data. So this is how the overall Grover search mechanics works. Yeah, these are some of the quantum computing research trends. See here, in 1998, after Grover published in the year 1996, then 98, then 2010, now in 2022, it is going very high because more research papers are coming. 4,000 documents per year. More, the quantum is growing. That means more research is, see, it is not my report, it is Elsevier reports. That means the research trends completely now focusing in quantum computing and the machine implementation that may help the future researchers to work more on quantum machines. So this is also a dangerous science for banking sectors and financial sectors. Like if more quantum power is there, then they can implement the quantum machines. Then we have to do more PQC, post quantum cryptography machines also we need to develop. And these are some of the applications of quantum. We can use quantum with AI and ML. With the machine learning power and AI power, we can generate more and more number of things. Then computational chemistry for drug design and development, and for cyber security and cryptography for more security purpose we can build. Financial modeling. Yeah, this I already told. Logic automation already they started doing. And weather forecasting, this is one of the best example we can do that. And these are some of the research domain and research opportunities, such as quantum error correction and fault tolerance, quantum algorithms. We have a lot of research opportunities are cryptography, quantum communication, quantum sensing, and quantum materials. We have a lot of demand here because most of companies, they are working with quantum, but they are not able to find the exact quantum specialist, quantum scientist for implementing their works. So there are huge number of companies now working with quantum AI. So you can also think about it, learn the quantum completely, and you can not completely because quantum cannot be completed. So we can at least some 0.5% we can learn, and we can explore some quantum technologies and quantum applications, so that we can at least we can say some of the things to the next set of juniors or your seniors or even the peers. They can understand about the quantum, they can implement in the same way. And these are some of the major players, that means the companies, the big giants, okay, tech giants such as Google, IBM, even Microsoft. They are having quantum computing machines, quantum computing lab with them for enabling the quantum machines. Quantum machines is not a simple machine, it is very costly as well. And there are some companies like Xanadu, HP, and D-Wave, quantum annealing, simulated annealing. Same like in AI, that's called simulated annealing concept. Same like in quantum annealing, there's companies working with D-Wave and QN and Cloud. And Trapped Ions, these are the companies that work with physical implementation of quantum computing. Even Alibaba Group is working, Intel, they're creating architecture because quantum processors they created. Even Google created on quantum architecture and quantum processor. Vara course, yeah, that name. Then Rigetti and other companies are doing. And these are some of the useful links. Now we will go through this. Up to now, any doubts you can ask, then we will see some links and we will learn some of the practical simulations of these algorithms. These are the references I have taken for these slides from NPTEL courses and also edX platform. Thank you. Now, any queries, any doubts you can ask. So this is my contact, and you can contact me for the possible collaboration, and also any doubts you can post a mail to me. I always welcome the collaboration and doubts so that I will learn something new. Okay, so any doubts you can ask, or else we can directly go for implementing the things, how the things works. Any doubts? Then you can unmute and ask. Yeah, you can unmute your mic and you can talk.
Thank you so much, sir, for providing a wonderful session, sir. So we are learning new things, sir, and we are trying to learn new things.
Okay.
Based on the what are shown your application, some of the applications, sir.
Okay.
So we are working that applications also, sir. Thank you, sir. Thank you so much.
Yeah, thank you, Mr. Vijay, for the feedback.
Thank you, sir. Thank you, sir.
So now, for 10 minutes, we will go with some simulation links. Till the session is on, it is not over. Participants, I think already that feedback link is giving, someone is saying feedback link is not working. Don't go away, just be there. And I will show you how to work or how to simulate this algorithms. Okay, let's connect to the session again. So participants, hope everyone seeing this screen, right? IBM Quantum Platform, quantum.cloud.ibm.com. That's the website. I'll also give this website in your chat box. You can try whenever you're having free time. Okay. Don't click. It's not a feedback link. It is for simulation and to see how the quantum, that DJ algorithm works. Okay. So you have to log in here, and we can also use Google Colab or Anaconda or Jupyter Notebook to perform these operations. So you need to know some basic idea about Python, and also you have to install this QS kit. Okay. And we have to give some basic codings, basic runtime command environment. Okay, it's like a command prompt, simply like a command prompt. Even we can see a lot of YouTube videos are there in this, how this Joshua algorithm works and how to practice this in IBM Quantum. Okay, whatever he explained, the same concept it is explained here also. And there what you have to do is, just it's a copy paste. Here you have to click copy code. This code will be copied. You have to keep it in your particular system and you can test it. So how to test it? See, map classical inputs to a quantum problem, and you can increase the number of qubits 1, 2, 3 like that, and you will get the output. And you can also include other packages for other simulators like this. So number of different varieties of informations available here in Deutsch algorithm. So if you see this, you can see the visualization also. So like that you can visualize this, and it is the overall count of 1 or 0, 1. And you can also see how the circuit diagram works. Ket of 0 and ket of 1 through the Hadamard gate, we are inputting to a unitary function called oracle. Then again double Hadamard gives the overall value. If all zeros, then f is constant. If only 1 is coming, it is f is balanced. Okay. This is Deutsch algorithm, and output will be like this. Suppose if you want to practically work on this, what to do is sign in. Then you have to sign in with your Google account, any account you can use, and you have to select your state, or else you can directly sign in with continue with Google also you can give. Okay, this is how we have to visualize the Deutsch-Joshua algorithm. Only we can visualize that. But if you want to give the qubits, and if you want to perform some operations like quantum computing, if you are doing some research, if you are writing a paper, and if you want to give, you can change some parameters and attributes as well as your procedures, functions, and you can generate your own graphs like this. Okay, next is Grover's algorithm. Same, again, QSKit, we have to download and we have to install. Then take any one of the Python online platform, Python IDE, okay, such as like I can type you that also. You can use either Anaconda IDE or Google Colab. Or Jupyter Notebook. So these 3 IDEs, in that one of the IDE we can take and we can work on it. Okay, I sent in chat box. And in Grover's algorithm also we can see the differences. How much Hadamard gates and what is, yeah, even some students, some participants asked about diffusion, right? Here it is clearly given. Operator, Grover's diffusion operator. It is using that Hadamard gates to perform the measurements. Okay, so this is how we have to understand this particular Grover's algorithm practical way. So here we are giving 2 qubits, Q0 and Q1, going to Hadamard gate, and the oracle function, again Hadamard gate, and XOR operation with Hadamard gate. So here diffusion operator is coming in, Z. That means this ZOR is diffusion operator. So it is a very big algorithm. You can step by step you can practice. Okay, all the codings are already available. This links also I will post it in your chat box. You can, in your free time, you can work on this. So I given 2 links for you, and also I given what are all the enablers like Python coding platforms. You can collaborate and you can, and also you can connect with me for any possible research collaborations or any doubts in quantum. I also shared my details. Okay, so you can work on it. Okay, now the session is open for interaction. Thank you very much. Yeah, now my session is completed. I request organizers.
Thank you, sir. We extend our sincere thanks to our esteemed speaker, Dr. Kaushik Shekharan, for sharing their valuable insights with us today. A special thanks to all organizing committee and the participants for active engagement. We look forward to seeing you at our next session. Thank you.
Sure, ma'am. Thank you very much. Thank you all the participants for your patient listening. And please work on quantum, because it is one session or two sessions won't make you to enable your complete idea in quantum. You need a complete understanding. You need to go through a lot of other ideas, other sessions, as well as you need to practice a lot actually, so that you will get a complete understanding on quantum. And even though we need more understanding on quantum, because every time we are understanding quantum algorithms or quantum computing, we always feel that we are not understanding. So that is the specialty in quantum. We need to learn more and more again in quantum. Thank you very much. Any doubts? Yeah, someone is raising hands.
Yeah. Hi, Kaushik Shekharan. Good afternoon.
Hi, sir. Good afternoon.
Yeah. May I know, could you please make it share a material
Yeah, sure.
for the yesterday and tomorrow today's material?
Sure, sir.
Make it easy to practice.
Okay.
Yeah, thank you. That's one.
Okay, sure, sir. Thank you. Any other doubts anyone have? Okay. Only they're asking feedback link. Okay. Some people are telling no, sir. That means no doubts. Yeah, Logamitra, tell me. Vijay Kalla, raise the hands. Yeah, you can tell one by one. Logamitra, you can start. I could not run QoS kit in Jupyter. Then go for next platform. Suppose.
Sir, can you suggest any textbooks regarding quantum computing, sir? If you are having, sir, can you share with me? It will be useful for
I will share some of the textbooks, sure. One of
Thank you,
my
sir.
professor, his name, Dr. Balamurli, given me one book. I forgot the author name. I will share with you. Please connect
Okay,
with
sir.
me with any doubts. You can WhatsApp me or mail to me. I will share the whatever reference material I have. And
Okay, sir.
also,
Thank you.
I am working with some labs, Quantum AI Lab. I am a consultant and a senior advisor for that company. I'm giving some of my knowledge to them. It's a knowledge sharing platform. So if you want, you can also collaborate with me in that. If you know some basics of quantum, we can work with some papers as well as some research work.
Okay, sir. Thank you,
Please
sir.
tell us your comfortable time so we can connect with you.
Yeah, probably evening 4 to 5 p.m. ma'am, because morning 10 to 4 I'm working as professor, so somewhere busy in academics, and 4 to 5 I am free, and again I will be driving my car, and from 6:30 to next morning I'll be busy with family, so
Okay,
4 to 5 is possible time.
sure. Please share the ebooks if you have.
Yeah,
We
sure,
can
ma'am,
start,
sure.
starting from there.
Sure, ma'am.
Thank you.
Thank you. Sir, how we can use a quantum computing financial portfolio optimization problem? Yeah, for a financial portfolio, like there is loop unrolling methods. We can use that because for most of the financial portfolios, such as even software project management scenarios, that is combining with quantum AA, a lot of optimizations going on that we can work out. But it depends upon the application where you use. It cannot be applicable for all the applications. Suppose, for example, even in Bitcoin mining, they tried quantum, but it is not working out because the block is having integrity specific. So that may not be possible. But we can work with other normal, without cryptocurrencies. If you are working for a specific financial portfolio, we can work on it. Again, stock market portfolio. So we can experiment it one by one. Yeah, but I will tell you, there are some quantum algorithms, they are trying to work for prediction based, quantum AA based. But the cost that would require to create that machines will more than what profit we got. So there is no point in using that. So once if the world stabilizes the quantum machines and affordable also, then everyone can go with it. As of now, it is completely initial phase of designing the quantum. So as of now, I think we have to work a lot to first understand the complete quantum. Then we can go each and every step by step for our progresses. Yeah, any other doubts? Or am I answering your doubt, Mr. Kamal Gavel? Yeah. Thank you. And next, Logamitra ma'am raised your hand. Dr. Bharat also raised the hand.
Yeah, how Kaushik?
Yes,
Like previously I asked that material now for yesterday and today's material.
I think you please contact coordinator. Ms. Madhuri ma'am, can you help them?
Sure, sir. I will forward it, sir.
Sure. Okay, ma'am.
Yeah, and also one more thing, Kaushik. Like you said that you have problem statement like work with papers, right?
Yeah.
Yeah, I'm working with you. Could you please share the like objective problem statement objective like that? We'll work on that one. Sure. We'll get paper to publish.
Sure, sir. Sure. We will have a connection. We will discuss about what problem statement we are planning to work. We will discuss.
Sure. We will wait for a update.
Sure, sir. Please connect
thank you
because
so much.
I may forget. Please remind me. Even just now, Akansha also told she will connect. So like that, if we connect, then we will work on what problem, what objective we are going to take. Networking is very important. Yeah, I understand. And also we have to work with not only one problem, because suppose I'm also working in IoT based systems. Suppose if you are interested, I can give some problems there. You can try to solve, and we can co-collaborate in our quantum research.
Sure, sir. Actually, I'm working with like that one in IoT devices. Like we can detect the malware detection now by using ML and DL. Using those methods, we are using those methods to detect the anomaly now.
Okay.
Yeah, now I inspired your speech. Like you said that previously, like quantum is efficient to do this one. Like that's why I connect with you. Maybe if it's possible, to share that research objectives to my mail ID.
Okay.
If it is possible, and also
I already given my mail ID and contact number. You please send your mail ID. We will discuss more on this.
Sure, sir. Sure. Can I share my mail ID? Which one now?
No, sir. I'm telling. I already shared my mail ID as well as my phone number. You can connect to me anytime. No problem.
Okay.
Yeah. Logamitra
Yeah,
ma'am is
got
waiting
it.
next. Yeah.
Got it, sir.
Yeah. Okay. Thank you, Bharat.
Good afternoon,
Okay, sir.
sir.
Thank you very much.
Yeah. Good afternoon, Miss Logamitra.
Sir, I could not run a quantum normal simple program in Jupyter, sir. Qiskit. Generally, I'm getting error like Qiskit AE or Qiskit simulation error. Do I need IBM API token, sir?
No. Actually, IBM recently they moved all the Kit to quantum, like quantum cloud. They have their quantum cloud. So they moved into cloud. We cannot have access directly to the IBM systems, IBM cloud. If we are doing that, they are asking more charges actually. This is a recent problem. So the Jupyter notebook is recently not coming. Yesterday, even I have a discussion with one of the other professor, Kranti, from Symbiosis University. He also told the same. And what we are planning is we are going to work with the command prompt, and we are going to simulate that. And with that simulated data, we are going to take for the next further research papers also.
Okay, sir.
And you can use other IDEs such as Anaconda. You can download, and that's called PIP command, right? Installing, and you can fetch that.
Yeah.
And
Okay, sir.
even Google Colab will be useful for doing that. Qiskit we can collaborate with.
Currently, I'm doing research in quantum, sir. So I could not run anything of the program. It is very difficult, sir.
Okay. So you are doing your PhD in quantum?
Yes, sir. Yes,
Very good. Okay. Then, okay, we will discuss some of the key points. You can connect with me. I will tell you some idea where to get some data and how to proceed. I will tell you because I have some collaborators abroad, but they will also help us.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Thank you. Yeah. Any other doubts? So if no doubts, Miss Madhuri, can we wind up session or?
Sir, okay, sir.
Okay, thank you. Thank you.
Yeah. Thank you very much.
Thank you, sir.
And we will see in some other session. Thank you very much.
Thank you very much.
Thank you. Thank you, ma'am. Participants, you can leave now.
Thank you so much, sir, for connecting with us.
Yeah. Thank you,
Thank
all
you,
the
madam.
participants.
Thank you very much, sir.
I expect some good communication also in the upcoming days. Like, please connect for any quantum related or even IoT. I'm also working in cloud. We will work for any possible collaboration either in research and also in academics. Thank you. All the best for everyone.
Sure, sir. Thank you so much.